Hello and welcome to our next chapter on chemical equilibrium. This is the last chapter in our class that we'll be talking about thermodynamics specifically, but this is probably the most important area of thermodynamics in terms of chemistry, and that is thinking about what are the thermodynamics of chemical reactions. Everything up to this point has been, either a single substance or mixtures of substances, but no reactions happening. Whereas in this chapter, we will be considering the thermodynamics of chemical reactions. Now, this is something you've already been introduced to and are familiar with, right? We're going to get to the idea of K, the equilibrium constant. But we're not just going to, argue that this is just some constant that exists that we should use. We're going to derive where this comes from and how it relates to the Gibbs free energy and chemical potentials that we have been talking about for the last several chapters. And so to start with, we're only going to consider gas phase reactions. We will move on to considering solids and liquids and solutions, of course, because those are, importance in chemistry. We use lots of those kind of reactions. But we will use gas phase reactions to start with, just so that we can use our ideal gas law behavior as a starting point, and then we can sort of build from there and see how things change as we move to other phases. And the other thing we're going to do for this first part of sort of deriving is we're going to look at a generic reaction. So it's a physical chemist's favorite reaction. We take nu A, this is our stoichiometric coefficient for our first reactant A, and it's going to react with B to form C and D. Oh, I forgot the stoichiometric coefficients. And again, everything's in the gas phase here. Now, of course, these are just generic gases. This is not boron and carbon, this and deuterium, right? These are just A, B, C, and D. And actually, let me stick with my notes here, just to make it less confusing. We'll use Y and Z instead, and that way I don't have this mixed up with my notes. Okay, and so if we're going to be looking at chemical reactions, the first thing we need to think about is how are we going to keep track of how far those reactions have gone. So ostensibly we'll start with our reactants. We'll start with certain moles of A and B, and those will turn into moles of Y and Z as our reaction goes on. And so to define this, for this reaction, we're going to use this variable that we call the extent of reaction. And we give this the Greek letter xi, which is drawn like this. Past classes have called this squiggles because it's sort of hard to draw or hard to say, but this is the Greek letter xi. And this is defined such that if we have n moles of A to start with, or our number of moles of A is equal to however many moles of A we started with, so Na0, minus our stoichiometric coefficient for A times the extent of reaction. So the extent of reaction is a number that will go from 0 to 1. So 0 meaning no reactions happened yet, 1 meaning it's gone to completion, and it could go anywhere in between. And we can define similar equations for our B and C, B, Y, and Z. So we'll have our initial moles of B, and for our reactants this will be negative that we are subtracting. And for our products, Y and Z, we could start with some of those products already present in our reaction mixture. That is a possibility, so we'll still include this initial moles of Y. And here we add, because we are producing the products. We assume the reaction goes forward, though of course it could go in reverse, depending. And then our extent of reaction would be negative instead of positive. But we take our stoichiometric coefficient times our extent of reaction, and then we define the exact same sort of equation for Z. And basically what the extent of reaction does is it allows us to scale everything by the stoichiometric coefficients to let us know sort of how far the reaction has gone. Again, a value of xi equal to 0 tells us that no reactions happened yet. xi equal to 1 would mean that all of our products have turned into reactants. All of our reactants have turned into products. So I said that backwards. And right, so, and just as a reminder, all of these terms here, these are just the initial moles that we have before any reaction has happened.